So to find the logistic model, we have the differential equation and the initial condition. We need to get k and y on either side of the equal sign. To solve for this, we need to take the integral. Do the integral of the side with dy, you need to use partial fractions. So this is going to make it equal to L equals the integral of a over y dy plus the integral of b over L minus y. Simplified, this is L equals a times L minus y plus b times y. When y equals 0, L equals a times L, which makes a equal to 1. Now to solve for b, you do the same thing where y equals L, so L equals b times L, making b also 1. So this is the integral of 1 over y dy plus the integral of 1 over L minus y dy. This is the natural log of y plus the negative natural log of L minus y. Simplified, this is the natural log of y over L minus y equal to kt plus c. Now to simplify this, you need to put everything to the e to those powers. Now that it is no longer to the natural log, y over L minus y equals c e to the kt. Now to solve for y, still you need to put everything to the negative 1 so that you can find c. So this is simplified down to L over y minus 1 equals c e to the negative kt, and then we add the 1 over. Now we put it to the negative 1 again so that we can get L over to the side where the rest of it is so that we can find y. So y equals L over c e to the negative kt plus 1. The initial condition is y at 0 equals y sub 0, so y sub 0 equals L over c e to the negative kt plus 1. So c equals L minus y sub 0 over y sub 0, which makes the logistic model be y equals L over L minus y sub 0 over y sub 0
times e to the negative kt plus y sub 0. The equation of initial value is dy dt is equal to 0.07y times the quantity of 1 minus y over 5 million. So the logistics model problem is basically the integrated version of the original initial value problem. A general form of this equation gives y equals 5 million times 25,000 all over 25,000 plus the quantity of 5 million minus 25,000 times e to the negative 0.07t. The initial amount of jellyfish is 25,000, therefore triple that is 75,000. So this gives you the equation 75,000 is equal to 5 million times 25,000 all over 25,000 plus 5 million minus 25,000 times e to the negative 0.07t. The next step is to simplify out the equation. This means moving the denominator over to the side with the 75,000 and then multiplying out the 5 million times 25,000. This gives you 75,000 times the entirety of the denominator set equal to 125 trillion jellyfish. The equation can then be simplified even more by dividing the 125 trillion by the 75,000. This helps simplify the side with the variable even more. The 25,000 that had been inside the parentheses previously can also be added over to the other side. This leaves the equation as 4,975,000 times e to the negative 0.07t is equal to 5,000,000 over 3 minus 25,000. From this point, the e can be isolated completely. This leaves the equation e to the negative 0.07t is equal to the quantity of 5,000,000 over 3 minus 25,000 all over 4,975,000. This can be simplified even more, leaving e to the negative 0.07t is equal to 197 over 597. Then, to isolate the variable, the natural log of each side is taken. This gives negative 0.07t is equal to the natural log of 197 over 597. So t is equal to 1.5839, which can be approximated to 2. This means that the jellyfish population is tripled 2 years from the initial date, which was 1972. 1,972 plus 2 equals 1,974, 1974. Therefore, the population of jellyfish will have tripled by the year 1974. In this problem, because we're solving for t, you set the population, 4.5 million, equal to the rest of your equation. This gives you 4.5 million is equal to 5 million times 25,000 all over 25,000 plus the quantity of 5 million minus 25,000 times e to the negative 0.07t. At this point, the denominator can be multiplied over to the side with the 4.5 million, which gives 4.5 million, or y, times the quantity of 25,000 plus 5 million minus 25,000 times e to the negative 0.07t is equal to the 5 million times 25,000. Then, the 4.5 million held by the variable y can be divided over to the 5 million times 25,000. From here, the 25,000 is subtracted on each side, which helps to isolate the part of the problem that has the variable attached. From here, you're left with 4,975,000 e to the negative 0.07t is equal to 250,000 over 9 minus 25,000. To get the e on one side all by itself, each side is divided by the 4,975,000. With this simplified, you're left with e to the negative 0.07t is equal to 250,000 over 9 minus 25,000 all over 4,975,000. To isolate t, the natural log of each side is taken, which produces negative 0.07t is equal to the natural log of the entire quantity of 25,000 over 9 minus 25,000 all over 4,975,000. To complete this, each side is divided by negative 0.07. So this makes t equal to the natural log of the entire quantity of 25,000 over 9 minus 25,000 all over 4,975,000. Then all of this is divided by the negative 0.07. After this is all calculated out, t is equal to 10.70076 years, which can be approximated up to 11 years. T is approximately 11, so you take 1972 plus 11 years equals 1983. Therefore, the population of jellyfish will reach 4.5 million in the year 1983.